Hello friends, now we will see one university question on calculation of deflection. This is for Annamal University for the year November 2014. It is a steel cantilever beam projecting 3 meters from your wall. It is loaded with UDL of 20 kilonewton per meter. We have to calculate the slope and deflection of the beam, and moment of inertia is given for the beam section. This is the cantilever beam. The span is 3 meters. The loading is 20 kilonewton per meter. Moment of inertia is given. I is equal to 7550 centimeter power 4. Let us convert this into meter power 4 because the length of the beam is in meters. Let us have the units consistently. For the sake of consistency, we will are converting this moment of inertia into meter power 4. Young's modulus is given as kilonewton per meter square, and this is assumed because they have mentioned it is T. It is 2.1 into 10 power 8 kilonewton per meter square. You can take either 2.1 or 2 into 10 power 8 kilonewton per meter square. The loading is in kilonewton, length is in meter. Therefore, we should have Young's modulus in kilonewton per meter square. It is either 2 into 10 power 8 or 2.1 into 10 power 8. Now we have to calculate the slope and deflection. In this cantilever beam, the slope, deflection or maximum at this free end of the cantilever, that is at B. First, we will calculate the slope at point B, that is theta B. Now, what about the slope at A? The slope at A is 0. Theta A is equal to 0 because the end A is fixed. And we have to apply the Mohr's first theorem of moment between the points A and B. What is stated by Mohr's first theorem? The difference between the slopes of any 2 points, that is theta B minus theta A, is equal to 1 by EI times area of the bending moment diagram between the points B and A. This is the first theorem of Mohr's moment area theorem. Theta B minus theta A is equal to 1 by EI times area of the bending moment diagram between the points B and A. Theta B and minus theta A. Here theta A is equal to 0. So if you apply the Mohr's first theorem for points A and B, theta B minus theta A becomes theta B is equal to 1 by EI times into, and what about the bending moment diagram? At any distance x from the point B, the bending moment is given by 20 into x, which is the load, and its arm distance is x by 2. 20 into x is the load, and it is acting at a distance of x by 2. Therefore, bending moment at any distance x is equal to 20 into x square by 2. This is the bending moment ordinate. Let us consider a small width of dx. Let us consider an elementary strip of small width dx. Now, area of the bending moment diagram. Ordinate is 20 into x square by 2 into the width dx. This is the area of the bending moment diagram for the small elementary strip. For the full area, integrate between the limits 0 to 3. B is the origin. So 0 to 3. Then 1 by A goes to the denominator and 20 by 2 into x square. Integration is s cubed by 3. So s cubed becomes 3 cubed. If you apply the upper limit by 3, then you are already having 2. 2 into 3 is 6. 20 by 6 into 3 cubed. Then upon simplification, this comes to 0.0057 radians. If you want to get it in degrees, multiply this by 180 and divide it by pi. This into 180 by pi will give you the degrees, that is 0.33 degrees. This is the value of the slope at the point B. We have applied the Mohr's first theorem between the points B and A. Now let us calculate the deflection at the free end B. Morse theorem, second theorem, gives the value of the vertical intercept between the tangents. Here we will consider the 2 points A and B. We will consider the bending moment diagram between the points A and B. And we will calculate the vertical intercept between the two tangents dropped from the point B. At A, the slope is 0 because it is fixed. If you draw a tangent, it will be horizontal. If you draw a tangent at the point A, it will be horizontal. Draw a tangent at B. Now, if you measure the vertical, this is one tangent, this is another tangent. Then this is the vertical intercept between the two tangents at point B. And that is denoted as YB. Morse theorem gives the value of the vertical intercept between the two tangents. This is one tangent drawn from A. This is another tangent drawn from B. Vertical intercept between the two tangents, that is equal to YB. This is given by Morse theorem, which happens to be equal to delta B, which is the deflection at the point B. And since YB is the intercept we are interested in, we have to take movement of the area of the bending moment diagram about the point B. Now, what is stated by Morse second theorem? Morse second theorem states the vertical intercept between the two tangents of the deflected curve is equal to 1 by EI times movement of the bending moment diagram. Here 1 by EI times, what is the moment of the bending moment diagram? 20 into x square by 2 is the ordinate of bending moment value at any distance x from A. And what is the area? This into dx, 20 into x square by 2 into dx. This is the area. And what is the moment? Then we are taking the moment about the point B. Therefore, into x, that will be the moment of the area of the bending moment diagram, delta B, which happens to be the vertical intercept between the two tangents YB is equal to 1 by EI times movement of the area of the bending moment diagram. This is the bending moment ordinate into dx. This is the area of the bending moment diagram. It is at B is the point from where we have to take the moment. Therefore, it is x. This into x is the moment of the area of the bending moment diagram. And B is the origin integrated between 0 to 3. Apply the upper limit. Then it becomes 20 by 2 into s cubed by this is s cubed. Already s square is there, x is there, s cubed. That means upon integration, it will become s power 4 by 4, and that is what it is. And upon simplification, this reduces to 0.0128 meter, which is equal to 12.8 mm. Now, you can ask one question: why can't we take movement about the point A? Now, this is one tangent drawn from A, which is horizontal. This is another tangent drawn from B. Suppose if this tangent gets extended, say up to point A. Now, what about the vertical intercept between the two tangents? If you take the vertical intercept of A, this is point A, this is one tangent, and this is another tangent, and this is the vertical intercept measured at A. This is the vertical intercept between the tangents. See, there are two vertical intercepts. This is the tangent drawn from the point A. This is the tangent drawn from point B. This is one vertical intercept. It is equal to the deflection delta B. Now, what about the other vertical intercept? This is the tangent drawn at A. This is the tangent drawn at B. Let it get extended up to this point. Now, this is the vertical intercept between the two tangents measured at A. This is the vertical intercept measured at A. Now, if you calculate this vertical intercept, then you have to take moment about the point A. But this vertical intercept is in no way related with the deflection delta B. Please understand. Whereas this vertical intercept measured at point B it is denoted as YB. It happens to be equal to delta B. And since this vertical intercept is what we are interested in, we have to take the moment about the point B. If you take moment about A, it will give the vertical intercept between the tangents at the point A, which is in no way related with the deflection value at B. Therefore, we have to take the moment about the point B. And the same thing can be obtained by the formula also. For the uniformly distributed load, slope is equal to WL cubed by 6EI. Upon substitution, you will get this value. And deflection at the free end, WL power 4 by 8EI. Upon substitution, you will get this value. This is by using the formula. I request you to visit my website, https://rgnsite.wordpress.com. There are about 500 university questions, detailed university questions and answers, covering various structural engineering subjects, RCC design, steel design, strength of materials, structural analysis volume 1, structural analysis volume 2, such as moment distribution method, slope deflection method, moving loads, influence lines, matrix methods, force method, flexibility method, deflection calculation. All these structural engineering subjects are addressed in this web blog. Please visit my site https://rgnsite.wordpress.com. There are about 500 university questions and answers, and the download is free, including the one which we have seen now, the deflection calculation. It is all available for free download. The download is free for all the subjects, for all the questions and answers, including the matrix methods. I also request you to go through my videos posted in my YouTube channel, RGN Class. Use RGN Class in the search engine. You will get the list of videos. Some of them will be mine, some of them will be irrelevant. You choose one of the videos in the RGN Class. There will be one icon R. If you press that icon R, then you will have this RGN Class complete list of videos. If you use the search engine RGN Class, you will have videos containing my videos as well as some other videos. Choose one of the videos with RGN Class. There one icon R will be there. If you press that icon, you will get all the videos of mine posted under the heading RGN Class without any mix of other videos. Thank you for your listening. Thank you.